Okay, I need to do a quick audio check. Can see the image. Okay. All right, that's good. Cool. Okay. All right. So greetings, YouTube. Greetings, scholars. What this is going to serve as our first full lecture for Morris Brown College. So basically, I'm going to be updating this playlist, periodically. And so my goal is to try to get these full lectures available as soon as possible, so that I'm trying to get ahead of you guys, so that you guys can get ahead, right? If these aren't available, then I can't expect you to get ahead, right? It would be nice if I could suppress this menu, but I haven't quite figured out how to do that. I don't think I want it there either. Let's put it here. Put it there for now. View settings and one single page. Okay. Yeah, they kind of changed the settings on me, so I'm trying to I hadn't found a rhythm all the way, but that's okay. All right. So again, for my students at Morris Brown, this is the book that we're going to be using. This is Blitzer, Thinking Mathematically, 7th edition. The PDF of this is available in Populi. So if you go to Populi, you click on like syllabus is on the right-hand panel, right? We can do that really quickly. So if we hop over to Populi, right? Not my open math, right here. So, oh no. Okay, that's good. All right, so if we go to our course, right here, and then we can click on syllabus, and on this right-hand panel, you see where it says Thinking Mathematically Chapter 1, right? You can click on that, and you'll find the copy of the relevant information there for this section, right? Okay. So we're going to be starting with Chapter 1. In Chapter 1, there are 3 sections that we're going to be working on. Chapter 1 covers problem solving and critical thinking, right? So Section 1.1 is on inductive and deductive reasoning, okay? And so also, anything that you see me writing, I'm going to make a PDF available. I think during our orientation, I went on and made a box link available in the dashboard in the announcement section. So when I'm done with this presentation, I'll make this link available, a PDF copy of anything that you see me writing. Let me try this at the top, because it's just totally irking me at the bottom here. But yeah, it should become available, and you can find it there. And if that doesn't work, we'll make a workaround. Some objectives here: we like to understand and use inductive reasoning, and understand and use deductive reasoning. Right? Oh, see, that doesn't work. Okay, hang on. Where can I put this? I guess I have to go to the side. Okay, maybe that's better. Okay. So inductive reasoning is the process of arriving at a general conclusion based on observations of specific examples. So some definitions: the conjecture hypothesis, the conclusion formed as a result of inductive reasoning which may or may not be true. Counterexample, a case for which the conjecture is not true, which proves the conjecture is false, right? So for inductive reasoning, that is starting with something specific and we're generalizing. Starting with a few specific examples, we want to see, can we generalize or make a generalization based on these few specific examples, right? So inductive reasoning is going from specific to a general conclusion, right? So the conjecture hypothesis, the conclusion formed as a result of inductive reasoning, which may or may not be true, right? Counterexample, a counterexample is where you find one example that shuts the hypothesis down, right? So a lot of times to disprove something, you only need one counterexample, but it depends on how it's kind of set up. But yeah. So strong inductive argument. In the random sample of 38 380,000 freshmen at 772 four-year colleges, 25% said they frequently came to class without completing reading or assignments. We can conclude that there is a 95% probability that between 24.84% and 25.25% of all college freshmen frequently come to class unprepared. This technique is called random sampling, discussed in chapter 12. Each member of the group has an equal chance of being chosen. We can make predictions based on a random sample of the entire population. A strong inductive argument. In a random sample of this many at this many schools. Okay. So I think this is just kind of introducing random sampling. Each member in the group has an equal likely chance of being chosen. Let's see what's on the next slide. So, okay, that was an example of a strong inductive argument. So let's look at an example of a weak inductive argument. Again, that's starting with something specific and we generalize it. So let me see, men have difficulty expressing their feelings. Neither my dad nor my boyfriend ever cried in front of me. This conclusion is based on just two observations, right? So his dad, her dad and her boyfriend, right? So then she generalized about all men based on two men. This sample is neither random nor large enough to represent all men. So the previous example was strong because it had a large enough sample size and it minimized, if not reduced, bias as much as possible, right? Where each individual had an equally likely chance of being selected, versus this one, she's making a conclusion. She's drawing a conclusion about a large population based on two outcomes, right? That's not enough. That's not a large enough sample size for this to be a strong inductive argument. So this is an example of a weak inductive argument, right? So using inductive reasoning, part 1 of 2, identify a pattern in each of the numbers, then use the pattern to find the next number, right? So here we have 3, 12, 21, 30, 39, right? Let me see. Are we adding the same thing each time? Well, let's see. 9 plus 3 is what? 12 plus 3 is 21. It looks like we are adding 9 each time. So if we're adding 9 each time, then what's the next one? Is that 48? Looks like the next one should be 48. I think we got it typed on the next line. And you see the 48 in the bottom right-hand corner, right? So the pattern here was that we were adding the same thing each time. Okay. All right. So let's see if we can find the pattern here. More than likely, we're not adding the same thing each time because look, 9 plus 3 is what, 12? But then that plus 9 is not 48, right? So let's try something else. We're not adding the same thing. Maybe we're multiplying the same thing. 3 times what? 4 is 12. Times 4 is 48. Times 4 is what? 160 plus 32 is 192, right? It looks like we're multiplying by 4 each time. So then 4 times 768, whatever that number is, right? And you can see we're multiplying by 4 each time. So then the next number is 4 times the last number, right? So part A in this example, what we call that, that's called an arithmetic progression, right? Because we're adding the same thing each time. In this example, this is called a geometric progression because we're multiplying the same thing each time. Okay. So what comes next in this list? Can we find a pattern, right? Are we adding the same thing each time? Well, let me see. First, we added 0. And if we add 0 again, we're not adding the same thing each time. Are we multiplying, right? First, we multiply by 1. Then we multiply by 2. Then by 3. No, we're not multiplying the same thing each time, right? So let's see if we can try to find a different pattern. It looks like we're saying like 1 plus 1 is 2. 2 plus 1 is 3. 3 plus 2 is 5. 5 plus 3 is 8. So we keep adding the previous, right? It looks like we keep adding the previous. I think this is called the Fibonacci sequence. So then what should come next should be 21 plus 13. It's what, 34? Should be 34. You see it there. Again, we're adding the previous term to generate the next one. Okay. Now, I may have been a little bit overconfident because I literally just got out of class with you all, and I decided to go ahead and at least make one recording available. I can feel myself fading rapidly. How many slides? I see my pages. Nope, I don't want that. Undo. Oh, what was that? So total of 20. Okay, that's all I wanted to know. Okay. Okay, so let's see. Inductive reasoning, more than one solution. Is this solution a wine goblet or two faces looking at each other? Right? And you can argue for either one. You could say it's a white wine goblet with a black background, or it's two faces with a white background. Right? 2, 4, and then question mark. What's the next number in the sequence? Well, in this sequence, we don't have enough information because we could be adding 2 each time, right? So the next number could be 6, or we could be multiplying by 2 each time, where the next number could be 8, right? So with that sequence, we weren't given enough information to identify the pattern. Okay, finding the next figure in a visual sequence. Describe 2 patterns in a sequence of figures. Use a pattern to draw the next figure, okay? So one pattern that we can see, it looks like what? It's going from circle, square, right? So we can anticipate, let me see if I can. So if it's going circle, square, I'm just going to do green, it's close enough. We can anticipate the next shape to be a circle. All right, we can anticipate something like this, all right? And it looks like we have a cross pattern. It's pretty standard. So I'm going to do this. This. Okay. Okay. So I think that's safe for now. Let's get some red. Okay. So let's see. If we follow the blank space, right? First, the blank space was at the top, then it was to the left, then it was bottom, then it was right. So then we can anticipate it to continue and be back at the top. So we should be back to the original. So it looks like we might have like a dot here, 2 dots here, and 3 dots here, right? So I think, so we can anticipate that to be the next image. Circle, square, circle. And then the blank tile was, first it was top, then it was left, then it was bottom, then it was right. So it should be back at the top, right? And it looks like the dots are following the blank tile, right? So again, we should be back to where we started. And you can see it there. Okay. So again, inductive reasoning is starting with specific examples, drawing a general conclusion based on some specific examples. So then if that's inductive reasoning, then deductive reasoning is the reverse of that. Deductive reasoning is a process of proving a specific conclusion from one or more general statements. A conclusion that is proved to be true by deductive reasoning is called a theorem. Okay, so deductive reasoning is starting with some general statement, jumping straight, being able to identify a specific example based on some general information. Right? It's basically the reverse of inductive reasoning. Again, inductive reasoning goes from specific and we generalize. Deductive reasoning is we start general and we can jump to any specific example that we want. Okay. So an example in everyday life of deductive reasoning, it says, let me see, one player to another in Scrabble, you have to remove those 5 letters. You can't use Texas as a word. Okay. Everyday situation in deductive reasoning, general statement, all proper names are prohibited in Scrabble. Since Texas is a proper name, therefore Texas is prohibited in Scrabble, right? So they started with a general statement and they, based on that general statement, they show that, this specific example has to be the case. And in this example, Texas is a proper name, so it's prohibited in Scrabble, right? Using inductive reasoning, apply the rules to specific numbers. You see the pattern. I mean, this one is just like, if we were live, I would kind of play a game. It's like, you choose a number. You can actually choose any number. It doesn't have to be 4, 7, or 11, but choose your favorite number. If you multiply the number by 6, add 8 to your answer, and then divide that answer by 2, subtract 4 from that quotient, then you should finish with 3 times your first number, right? That's the pattern. If you follow this, so because they want us to use inductive, they started with specific examples, and the conclusion is, the general statement is, we're going to finish with 3 times whatever we started with, right? And you can test it out. Choose your favorite number, multiply by 6, add 8, then divide that answer by 2 and subtract 4 from your quotient, and you should finish with 3 times your original, right? And so if we're going to use deductive reasoning, if we're selecting a number, we're going to just let it be n. If we multiply it by 6, so now we're going to have 6n. If we add 8, so now we have 6n plus 8. Then we say that answer divided by 2, which simplifies down to 3n plus 4. And then if we subtract 4, we finish with 3 times whatever we started with, right? And then the question is, does this agree with our inductive hypothesis? Yes, that's what we say. I don't know. I'm struggling to get my words out. I think I'm tired. And which is good, because we made it to the end of this section, right? Okay. So I'll go ahead and do the next section momentarily. Let me see. Can I just add a page? How do I add a page? I go here. Can I copy? Or I can just leave it. That's fine. Okay. So so that was inductive and deductive reasoning. And on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. The next section will be available momentarily. Take care. Peace.